The moment it appeared, it shook the world. When the project was completed, even the workers did not know what they had built. It wasn't until 1954, when BRDA lifted the veil of secrecy, that this technology was publicly revealed. The nuclear reactor was originally a military product developed during the Cold War. Today, it supplies about 10% of the world's electricity, but controversies surrounding it have never ceased. Today, we will explore its working principles, safety measures, and manufacturing process for a clearer understanding. First, let's look at its structural diagram. Scientifically known as a nuclear reactor, its pressurized water cooling system acts as the first circulation loop to generate steam. This system, along with auxiliary and supporting equipment, is collectively referred to as the nuclear system. We will not delve into details here, but the following sections will provide a more in-depth introduction. Now, we move on to the main topic, the pressure vessel. It must operate within a limit of 160 atmospheres. Countries treat this as the final stage of a marathon and carry it out with extreme caution. To understand the manufacturing principles, let's examine a 3D model. Unlike conventional structures, the reactor body must be integrally rolled from steel plates to minimize the risk of thermal cracking that could lead to structural deformation. After achieving the perfect shape, both sides are cut off and then rotated along the same axis. Next, the cylindrical steel block is pressed into a massive circular disc. The center is then perforated with hydraulic assistance to insert the rotating shaft. Through this series of processes, we can see the detailed image of the reactor body when split in half. The pressure vessel requires 5 large steel rings with wall thicknesses of up to 20 centimeters. Each ring must undergo this process before proceeding to the welding stage. This is also the most stringent phase. What we see here is an automatic welding device with an integrated heating system. Above it is the heating plate, while below is the synchronously operating welding torch. First, the device heats one side at an extremely low speed. When the temperature reaches the standard level, the torch immediately welds the preheated spot. But why is preheating necessary during welding? 2 important terms are preheating and post-weld heat treatment. Preheating reduces solidification stress and cold cracking, keeping the weld at a high temperature. When the welding wire melts, it adheres better to metal surfaces of similar or higher temperatures, ensuring strength and preventing explosions due to stress differences. Looking at the reactor's massive size, you can guess that forming it in a single process is impossible. Therefore, the 20-centimeter thick steel is processed in segments. Once the reactor body is complete, the lid is fabricated. The large steel tubes, bigger than a human thigh, are used as the reactor lid or base. Their central sections are cut out and then heated in an electric furnace for several hours. Once they reach the standard temperature, the steel is pressed horizontally by a hydraulic press exerting tens of thousands of tons of force. These steel plates are manufactured according to seamless steel tube standards, offering superior thickness and optimal density. After a second round of heating, the steel plate is formed into a circular shape. At this stage, we have the basic structure of the reactor lid. However, a crucial detail is that the lid must be pressed into place in a single attempt. Pausing midway is not allowed. If misaligned or inaccurate, the entire product is discarded. During quality inspection, high-power X-ray scans detect gas pockets, cracks, or substandard welds. Only when the reactor meets all standards can the steam generator manufacturing process begin. The steam generator plays a crucial role in heat transfer between the first and second circulation loops. It uses a nickel-chromium alloy for heat-conducting tubes. Before 2018, China faced difficulties in producing this alloy, but through collaboration with research institutes, they successfully developed alloy 690 as a replacement. These heat transfer tubes not only conduct heat, but also prevent radioactive leakage into the second circulation loop. Due to safety concerns, despite the high research costs, countries prioritize developing this technology rather than relying on imports. When assembling the steam generator, engineers must work in the confined space of the metal chamber. Thus, only those with suitable physiques are selected. Once the structure is completed, the nuclear reactor's steam generator platform takes shape. However, its durability must be tested by injecting it with 245 megapascals, approximately 250 att, of pressure to evaluate its endurance limit. Note that the reactor's actual operating pressure is only about 160 attomet. This higher test pressure ensures safety. Currently, over 65% of nuclear power plants worldwide use Russia's VVR-1200, a third-generation pressurized water reactor. Its structure is protected by an internal 120 centimeters thick reinforced concrete layer and an external 80 centimeters thick layer, ensuring no radiation leaks. Nuclear power plants also have their own defense systems capable of withstanding strong earthquakes and external impacts. As of Q1 2024, there are 413 operational nuclear reactors worldwide, demonstrating the safety of this technology. A nuclear power plant is a massive-scale project involving complex operational systems, but all efforts are aimed at ensuring a sustainable and safe energy source. Let me know if you need any modifications or refinements.
These powerful machines are the heart of hydroelectric power plants, transforming the kinetic energy of flowing water into electricity that lights our homes and powers our industries. The process of creating a hydroelectric turbine is a complex ballet of engineering, manufacturing, and assembly. From the initial design phase, where engineers meticulously calculate the turbine's dimensions and specifications to harness the specific water flow and head, to the final installation at the hydroelectric site, each step is crucial in ensuring the turbine's efficiency and longevity. Join us as we explore the fascinating journey of a hydroelectric turbine, from concept to completion. The genesis of hydroelectric power can be traced back to 1882 in Appleton, Wisconsin, where the world's inaugural hydroelectric central station was constructed. This pioneering facility, established just 3 years after Thomas Edison's incandescent light bulb, generated a modest 12.5 kilowatts, sufficient to illuminate 2 paper mills and a residence. However, the potential of hydroelectric power was quickly recognized, and its development surged rapidly. Despite early installations being relatively small, delivering only a few hundred to a few thousand kilowatts. By the 1930s, units with capacities exceeding 100,000 kilowatts began to emerge. One of the most notable examples of this early large-scale development was the Hoover Dam on the Colorado River, which commenced operations in 1936 and eventually incorporated 17 Francis turbines capable of producing between 40,000 and 130,000 kilowatts each, as well as two 3,000 kilowatt Pelton wheels. Water turbines are broadly categorized into impulse turbines, suitable for high water heads and low flow rates, and reaction turbines, typically employed for heads below 450 meters and moderate to high flow rates. The most common types within these categories include the Pelton impulse turbine and the Francis, Propeller, Kaplan, and Darius reaction turbines. While both horizontal and vertical shaft arrangements are possible, the latter is more prevalent. The specific design of a turbine can vary widely to accommodate diverse local hydraulic conditions. Today, hydroelectric installations, driven by the efficiency and sustainability of water turbines, play a crucial role in generating electricity worldwide. Giant electric motors, the titans of industrial machinery, are indispensable in a wide range of applications, from power generation to manufacturing. These colossal devices convert electrical energy into mechanical work, driving everything from ships and mining equipment to massive factory presses. Their design and engineering are a testament to human ingenuity. A team of experts meticulously crafts each motor's specifications, considering the unique demands of its intended use. Advanced computer-aided design (CAD) software allows engineers to visualize and refine the motor's core components, the rotor, stator, and housing. These designs must balance power output, efficiency, and the ability to withstand harsh operating environments. Material selection is equally critical. The choice of materials directly impacts the motor's performance, durability, and overall lifespan. Engineers and material scientists collaborate to identify materials that can withstand the extreme temperatures, loads, and other demanding conditions encountered in industrial settings. Rigorous testing ensures that these materials meet the stringent requirements for reliability and safety. The intricate dance of crafting giant electric motors begins with the precise fabrication of the rotor and stator, the motor's core components. These components are meticulously machined from high-quality materials to ensure optimal performance. Copper or aluminum wires are then meticulously wound onto the stator to create electromagnetic coils. The winding pattern is critical in determining the motor's efficiency and power output. Once assembled with bearings to facilitate smooth rotation, the motor undergoes rigorous testing to verify its performance, efficiency, and safety. The installation of these behemoths, whether in the heart of a massive ship or the bustling factory floor, demands specialized expertise and skilled technicians. Built to endure, these giant electric motors require regular maintenance to maintain their peak performance. Power generation, the process of producing electricity, encompasses a diverse array of technologies. From the venerable steam boilers, dating back over a century, to the more recent wind turbines, these methods have evolved to meet the world's growing energy demands. Interestingly, the concept of using steam boilers and windmills to power machinery and grind grain predates their application in electricity generation. Today, however, these technologies primarily serve the purpose of producing electricity. The fundamental principle behind most power generation equipment involves the rotation of a mechanism within an alternator. The specific method used to spin this mechanism varies depending on the underlying technology. Gone are the days of simply knowing electricity comes from power plants. Let's delve deeper and explore the fascinating process behind it. Imagine a spinning motion, like a giant toy top, being channeled into an alternator. This marvel of engineering, akin to an electric motor but in reverse, utilizes that motion to create electricity. Motors use electricity to spin, while alternators harness that spin to generate electricity. In fact, many motors can even be rigged as makeshift alternators in a pinch. Inside an alternator lies a captivating dance between two key components, the stator and the rotor. The rotor, designed to generate a magnetic field, spins within the alternator. The stator, a stationary casing, houses intricately wound copper coils wrapped around a hollow iron core. As the rotor whirls, its magnetic field twirls in sync. This mesmerizing rotation induces an electric current within the stator's copper coils, and voila, electricity is born. This current is then collected and distributed through the power grid, reaching our homes and industries. Power generators take this a step further. Think of them as miniaturized power plants, self-contained units housing an engine and, you guessed it, an alternator. These versatile units can range in size, from a mighty tractor trailer to a compact suitcase, catering to various electricity needs. Fuel options are equally diverse, with engines readily available for diesel, gasoline, biofuels, natural gas, and more. These larger generators find their place in a multitude of applications. They can be the main source of power in remote locations, like military bases, or act as reliable backups in case of grid failures. Hospitals and data centers, where even a flicker of power loss is unacceptable, rely heavily on standby generators to keep things running smoothly. So, the next time you flip on a switch, remember the intricate ballet taking place within power plants and generators. These marvels of engineering, akin to giant electric motors in reverse, play an indispensable role in powering our world's vast network of machines and industries. Thank you for your participation today. We hope you found our discussion engaging and informative. As you continue your journey through the ever-evolving landscape of technology, may curiosity be your guiding star. Until we meet again, keep exploring, experimenting, and discovering the endless possibilities that innovation offers.